Okay, take a quick second and just look down at your shirt, your pants, or, well, whatever it is you're wearing right now. What exactly is that physical matter covering your body? I mean, we put clothes on every single day, right? But we rarely stop to actually think about the microscopic structures and the kind of crazy origins of the fabrics resting right against our skin. Are you wearing the seed hairs of a plant, the extruded protein from an insect, or, hey, maybe it's a thermoplastic polymer cooked up in a laboratory? Hello and welcome to this explainer. I am absolutely thrilled you're joining us because today we are going to demystify the origins of our everyday clothes. We're going to finally decode those super confusing clothing tags and explore the fascinating science of textile fibers. We'll be tracing their whole journey, all the way from natural, organic origins out in the field, straight through to cutting-edge laboratory synthetics. So let's dive right into it. So here is our roadmap for today. We'll be covering 1. The anatomy of textiles. 2. Plant-based natural fibers. 3. Animal-based natural fibers. 4. The man-made fiber revolution. And finally, 5. High-performance superfibers. All right, let's kick things off with part 1, the anatomy of textiles. Before we even try to categorize our clothes, we really need to understand the fundamental microscopic rules of what actually makes a fiber, well, a fiber. Think about the number 100 for a second. By definition, for any unit of matter to be considered a textile fiber, it literally must be at least 100 times longer than its thickness. That is the absolute baseline rule of textiles. It's this extreme ratio of length to width that actually allows these tiny units to be spun, drafted, and twisted together to form the yarns that eventually become our fabrics. Kind of wild to think about, right? And if we zoom in even further, past that 100-to-1 ratio, we hit the molecular level. The basic building block of literally all textile fibers, whether we're talking about cotton, wool, or silk, is the molecule. Specifically, these molecules link up to form these really long chains that we call polymers. So the absolute crucial takeaway here is that a fiber's polymeric structure, its unique molecular chain and chemical makeup, dictates absolutely everything about how that fiber behaves. It determines how strong it is, how it stretches, and exactly how it feels on your body. To keep all of this organized in our heads, let's take a look at the fiber family tree. This tree brilliantly illustrates exactly how we classify textiles. First off, we divide them right down the middle by their origin, natural versus man-made. Then we get a bit more specific and classify them by their chemical composition. So out in nature, plants give us cellulosic fibers like cotton and jute, while animals provide protein fibers like wool and silk. On the flip side, over on the man-made side of the tree, we've got regenerated cellulosic fibers like viscose rayon and entirely synthetic polymers like polyester and nylon. Definitely keep this mental map handy as we move forward. Moving right along to part 2, plant-based natural fibers. So we're pivoting to the organic world now to focus first on humanity's incredible ability to harness plant-based cellulosic fibers. Did you know cotton is actually the seed hair of the cotton plant? What makes cotton so massively popular across the globe is its hygroscopic nature. Now, all that fancy word means is that it can naturally absorb around 8.5% of its dry weight in moisture. This gives it the amazing ability to soak up our perspiration. Plus, because of that moisture retention, it totally prevents the fabric from developing static electricity. It also conducts heat energy really well, which is exactly why you instinctively reach for a cotton t-shirt when it's hot and humid outside. Now, compare that super soft seed hair to the jute plant. Unlike cotton, jute is actually obtained from the stem of the plant. While it is still cellulosic and definitely absorbs moisture, it behaves completely differently. Jute has excellent strength, but very low elongation. Basically, it does not stretch at all. Because it has such a rough, stiff handle, we really don't use it for clothing. Instead, its massive strength makes it the absolute perfect choice for things like heavy sacks, bags, and carpets. And rounding out our major plant fibers is flax, which you probably know best as the source for linen fabric. Flax fibers are thick and incredibly strong, but they possess a highly stiff handle. And this actually perfectly illustrates a really key property. Because of this inherent stiffness, flax creases incredibly easily compared to cotton, even though structurally both are made of natural cellulose. It's why linen suits look so effortlessly rumpled. Which brings us to part 3. Animal-based natural fibers. Here, we are officially leaving the plant world of cellulose behind and entering the world of natural proteins, which have highly tactile and really unique sensory characteristics. Honestly, the absolute best way to understand animal fibers is to look at the ultimate contrast between wool and silk. On one hand, you have the structural wavy chaos of a sheep's fleece, specifically designed by nature for rugged insulation. On the other hand, you have the flawless, continuous elegance of a filament extruded by a spinning insect. It's like night and day. Let's break these two down. Wool has these tiny microscopic scales on its surface, but the real magic lies in what we call its natural crimp, that wavy, almost zigzag structure. This crimp provides natural bulkiness and creates millions of tiny air spaces within the fabric. Since air is a phenomenal insulator, it traps your body heat. But okay, here's the most fascinating part. Wool actually gives off a small, steady amount of heat while it's absorbing moisture from the air. Yes, you heard that right. This active heat-releasing property is totally unique among fibers and is the exact reason why wool keeps us so remarkably warm in the freezing cold.
In stark contrast, we have silk. Instead of short, crimped hairs, silk is actually extracted from the cocoons of silkworms as a single continuous strand known as a filament. Get this, a single filament can be an astonishing 700 to 1,200 meters long. That's more than 10 football fields. In its raw state, two silk filaments are stuck together by a protein called sericin, or silk gum, which actually makes it feel pretty coarse. But when we strip that gum away through a process called degumming, we reveal that incredibly smooth, highly lustrous, and elegant silk fabric we all know and love.
Now for part 4, the man-made fiber revolution. For literally millennia, humans only used what nature directly provided. But eventually, we learned to mimic nature. Humanity's very first real hack resulted in viscose rayon. This is what we call a regenerated cellulosic fiber. Scientists figured out how to take cellulose from wood pulp, dissolve it into a thick, viscous, liquid alkali cellulose solution, and then mechanically spin it into a fiber. Because its underlying chemical composition is essentially the exact same as cotton, it brilliantly mimics cotton's properties, including its ability to absorb moisture and perspiration. The result? A highly comfortable, breathable fabric born entirely from a machine. A real game changer. But of course, we didn't stop there. We went a step further into purely synthetic polymers. When we look at synthetic polyester and nylon fibers under a microscope, notice how drastically different they look from the organic, chaotic crimp of wool or cotton. They are flawlessly smooth, engineered with absolute, ultimate precision. Both are what we call thermoplastic, meaning they can actually be shaped or molded when heated. This allows us to heat set them into permanent shapes, like pleats that never wash out. So the crucial point here is how we can intentionally engineer their properties for very specific utilities. Polyester is incredibly strong and highly hydrophobic, meaning it hates water and only absorbs about 0.4% moisture. Because of this, it dries incredibly fast and naturally resists wrinkles, making it the perfect durable fiber to blend with cotton for things like uniforms and crisp shirting. Nylon, on the other hand, is engineered for supreme elasticity and excellent abrasion resistance. That stretch and undeniable toughness make nylon the absolute gold standard for activewear, swimwear, and even heavy-duty ropes. We even learned how to engineer synthetic fibers to directly mimic our favorite animal proteins. Take a look at acrylic fibers, which are spun from an acrylonitrile polymer. There is a deliberate, slight wave engineered right into the strands. That manufactured wave perfectly mimics the natural crimp and bulk of winter wool that we looked at earlier. It gives acrylic a beautifully soft handle, making it a lightweight, synthetic, and often much cheaper alternative for knitted sweaters and warm shawls. And finally, part 5, high-performance superfibers. We have now arrived at the absolute pinnacle of textile engineering. We're looking at fibers that go far, far beyond everyday fashion. The applications for these superfibers are, frankly, intense. We aren't talking about knitting a cozy winter sweater anymore. We're talking about fabrics designed to literally stop a speeding bullet in a Kevlar vest. We're talking about textiles that can withstand the roaring, intense flames of a burning building to protect our firefighters. We are even talking about fibers structurally sound enough to be used in the aerospace engineering of the actual aircraft we fly in. These textiles protect humanity in the most extreme, unforgiving environments imaginable. To achieve this level of performance, scientists have commercialized ultra-high molecular weight polymers. We're talking about materials like carbon fibers, Dyneema, and aramid fibers, which you might actually know by their commercial names like Kevlar or Nomex. These represent the absolute modern high-performance frontier. They boast unimaginable strength, total resistance to harsh, corrosive chemicals, and the ability to withstand extreme temperatures without degrading one bit. They are, quite literally, the superheroes of the textile world. Which brings us right back to where we started, but this time we're looking forward. From harvesting plant seeds and insect cocoons, to extruding wood pulp in a factory, to engineering bullet-stopping superpolymers, the technological evolution of the fibers we wear has been staggeringly rapid. So the next time you put on a shirt, just check the tag and ask yourself, as science continues to blur the line between nature and the laboratory, what exactly will your clothes be made of tomorrow? Thank you so much for joining me on this explainer. Keep learning, stay curious, and I'll see you next time.